because it's statically indeterminate, I want to start with that internal cut where I draw the picture cutting at the extreme right, or just before the extreme right, and then finding my m of x. So I'm cutting just to the left of C. I have my internal moment m. And then the forces and the couples acting on this, I have a force at A where I have that pin. But here I don't know what it is. I'm just going to call it A for right now. I have my applied load of P, which is 4,000 newtons. It's going to be located 1 meter away from A. I have the roller in the middle at B, another meter away from that applied load of 4,000 newtons. Another applied load of 4,000 newtons, and I can't see C in the picture because I'm cutting just to the left of it. So in this case, I have those two unknown reaction forces, and I have two applied loads of 4,000 newtons each. So using this internal cut free body diagram, I want to get my equation for m of x, or I'm going to first take the moments around that cut surface, which I call point Q. So I have m of x. And then what else is going to contribute to the moment around point Q from this internal free body diagram?
A times x.
Right, so minus a times x. Remember, point Q is always x away from the extreme left side. So A is going to be multiplied by the x distance, and it's negative because it is clockwise around Q. Right, we have the other applied load, and this is where we use the singularity function, because it has that offset of 2 meters from the left-hand side. So we don't want it to appear if we're cutting to the left of B, and that will be x minus 2 away from point Q if we're cutting to the right of B. Right, plus 4,000, x minus 1. And then the other 4,000 times x minus 3. M of x is the same as EIV double prime. So I just want to take this and solve it for mx. So I'll have ax. I'm going to rearrange this a little bit. 4,000 x minus 1 plus b x minus 2 minus 4,000 x minus 3. I integrate it to get my slope equation. So I have v prime, which is my slope. And I integrate a second time to get my deflection equation. So if we count right now the number of unknowns we have, we don't know A, B, C1, C2. We have 4 unknowns. We also don't know the reaction at C, which we'll solve along the way here. We have a total of 5 unknowns, so we need a total of 5 equations to solve for those 5 unknowns. So using this, still looking at our deflection equation, let's find our boundary conditions to get some of those equations. We're going to have a deflection boundary condition at A, B, and C also. In this case, what do we know the deflection is at A, B, and C? 0. Right, 0 at all of them. So V of 0 and V of 2 and V of 4 are all 0. So 3 boundary conditions. So usually the first one, the easiest one, is if we do have a x equals 0 boundary condition. So V of 0 is equal to 0. So that's the same as 1 over EI times this evaluated at x equals 0. So when we plug in 0 here, this term drops out. This one, this one, this one, this one. We're just left with C2 as the only non-zero value And because the boundary condition is equal to 0, I can multiply through by the EI, and that will drop out also. So I'm left with C2 is equal to 0. We know the deflection at x equals 2 is also 0. So it's going to be 1 over EI times this expression, now evaluated at x equals 2. So we'll have the first term, we'll have a over 6, 2 cubed, minus 2,000 over 3 times 1 cubed, which is just 1. This term will drop out, this term will drop out, and then this will be 2 times C1. And as before, it's equal to 0, so I can multiply through by EI, so that will drop out. In this equation, I've already used this one. I have one equation, I have A, and I have C1. So I have to make more equations to be able to solve for these unknowns. So my third equation is now my third boundary condition for V4, or V of 4. It's another deflection equation. I use the same equation again, but evaluated at x equals 4. Have that. Cubed. All right, so if we look at the third equation, we have A, we have B, and we have C1. Equation 2, we have A and we have C1. So we have 3 unknowns between the 2 equations. We have to get more equations to be able to solve this at this point. But any questions on applying the 3 boundary conditions now for these 3 equations? We'll still get 2 more to solve for all 5 of our unknowns. Right, now, I saved for the end my external free body diagram, which will give me the 2 more equations I need to solve for my 5 unknowns. And I'll take the sum of moments around C in this picture. I'll get 4,000 minus 2B plus 3 times 4,000 minus 4A. So this is where by hand, this is going to get not so great to do, because between equations 5, I have A and B, I have equations 2 and equations 3. I can solve for A, I can solve for B, and I can solve for C1. But I have 3 equations with 3 unknowns. It's not that easy to do by hand. I could use a solver or do a matrix inverse or elimination rule, whatever I want to do. But at least if I count my 5 equations, I can now solve for all 5 of my unknowns. One of them I already know, C2 was 0. So again, taking equations first 5, 2, and 3, I can find that A is 1250 newtons. B is 5500. And C1 is going to be negative 500. I put that into my equation 4. And that will tell me that C is also 1250. So that's just solving those 4 equations, or 3 equations simultaneously, plugging that result into my 4th equation. So now I can answer the question of what is my deflection equation going to look like now that I solve for these unknowns. Plugging in what I know now, I know the value of A is 1250. The value of B was 5500. And the value of C1 was negative 500.